Thank you. All right, good morning, everyone. My name is Keshav, and I'm a PhD student working at OSU with Professor Jason Weiss and Professor Burkanishkar. And today I'll be presenting on their behalf. The topic of my talk is transport in concrete and how we can use formation factor effectively. So in this presentation, I'll give you a brief introduction into the current state. Then we'll look at how formation factor is a material property. And then we'll look at how formation factor can be linked to transport in concrete. Finally, we'll look at how formation factor can be used as a good quality control tool. In recent years, it's becoming more and more common to measure electrical resistivity as an indicator of the performance of concrete. This is great. Measurement of resistivity is quick, it's relatively inexpensive, and the equipment is usually quite portable. My colleagues have hinted and talked about the testing details in other talks, and if anyone would like some references on the testing methodology and details, please feel free to shoot me an email and I can send you some references and sources. This talk particularly is about why we would suggest specifying formation factor to be the performance parameter to specify and why we do not recommend specifying resistivity. Well, this is because resistivity is not a fundamental measure. The resistivity of concrete is influenced by several factors such as the temperature of the sample at measurement. Usually a higher temperature leads to a lower resistivity. The resistivity of concrete is influenced by the degree of saturation of the concrete. Sometimes the resistivity has geometry correction factors. The resistivity is influenced by leaching of ions, and the resistivity depends on the pore solution resistivity itself. But the microstructure of concrete does not depend on these parameters that I've listed. Hence, we need a better parameter to specify something that's related to just the microstructure of concrete. Let me try to illustrate this with an example. Let's do a thought experiment. Consider we have two cylinders of concrete. Assume that we cast the concrete such that the microstructure is identical, meaning the porosity and the pore connectivity are exactly the same. The only difference between the two concretes is the alkali content of the cements used. The green concrete, let's say, is made with a cement of a lower alkali content, and the yellow concrete is made with a cement of a higher alkali content, let's say 1.4%. That's the only difference between the two concretes. Let's calculate their resistivities. The resistivity is related to the pore volume, pore connectivity, and pore solution resistivity, and it can be calculated using the formula shown on the screen. We can know the pore solution resistivity because we know the alkali contents and the cement composition for both concretes. Now, if we do this exercise and we calculate the resistivity of the two concretes, the green concrete would have a resistivity of 175 ohm meter, and the yellow concrete would have a resistivity of 32 ohm meter. But the microstructure is identical. We can see that specifying resistivity is therefore not the right approach to obtaining the same performance. Now, let's look at the formation factor. The formation factor of concrete is defined as the inverse of the product of porosity and pore connectivity, and therefore as such is only a function of the microstructure of concrete. The formation factor can be measured by normalizing the bulk resistivity with the pore solution resistivity, which makes it independent of the pore solution resistivity. Now let's repeat this exercise with the formation factor. When we calculated the resistivity of the green concrete, we found it to be 175 ohm meter. And when we calculated the resistivity of the yellow concrete, it was 32. And the resistivities were different. But if we calculate the formation factor, we find that the formation factor is exactly the same at 500. Therefore, since formation factor depends only on the microstructure, it should not be a surprise. And since the pore solution resistivity does not affect it. Hence, specifying the formation factor is a better approach than specifying resistivity. That is the first takeaway of this presentation. Formation factor is a microstructural descriptor. It doesn't depend on the temperature and it doesn't depend on the pore solution characteristics. It only depends on the microstructure. To underscore the point again, formation factor is a microstructural descriptor, and the microstructure can be described fairly well with the formation factor. Because of that, it's better to specify than the resistivity. The second goal of my talk is to demonstrate that formation factor can be fundamentally related to transport in concrete, which means it can be related to several existing tests such as RCPT, diffusion, water absorption, etc. And as such, by measuring the formation factor, we can have the results of these tests automatically. Let's start with the RCPT. The charge passed can be related to the formation factor and the pore solution resistivity through simple integration. The plot on the right shows the charge passed for a given formation factor and pore solution resistivity. If we know the formation factor, we needn't run the RCPT test. This is advantageous since there are inherent errors in the RCPT test, for example, the sample overheating. It's also better because the pore solution resistivity can have a huge impact, as we saw before in the results of the RCPT test and the resistivity, even if the microstructure is the same. The formation factor is therefore better to specify since it's quicker to measure and it's independent of the pore solution resistivity. The formation factor can also be related to ionic diffusion in concrete. The effective diffusion coefficient can be calculated in a straightforward manner as the formation factor is defined in terms of the diffusion coefficient. Typically though, we don't use the effective diffusion coefficient as it doesn't account for binding. But no worries, the apparent diffusion coefficient which does account for binding can also be calculated from first principles. The equation on the screen is the closed form solution for the apparent diffusion coefficient, which is obtained from the first principles for any binding isotherm and microstructure. The plot on the right shows the chloride concentration versus depth in concrete for two binding isotherms for which this equation has been solved, and the experimental results are also shown as the markers. And as we can see, it works pretty well. And that's because these equations are derived from first principles. There's a fundamental relation between water absorption and formation factor can also be established. But before that, let's talk a little about water absorption in concrete. The figure shows the mass change of a cylinder of concrete immersed in a bucket of water. This is colloquially called the bucket test in AASHTO PP84. And it's basically as simple as it sounds. Take cylinders of concrete and immerse them in a bucket of water. Once we immerse the cylinder of concrete in a bucket of water, the matrix pores, which are the smallest pores, the gel pores, the capillary pores, and the pores due to chemical shrinkage, they fill up relatively quickly within the first few hours. The air voids, on the other hand, take weeks to months to years to fill up. The degree of saturation at which the matrix pores are filled is called the Nick point or the matrix saturation point. We can see that there are two different rates of water absorption. One when the degree of saturation is lower than the Nick point, and one when the degree of saturation is higher than the Nick point. The rate of absorption of water in both cases can be related to formation factor from first principles. The equation that I'm showing on the screen is derived from first principles, and it relates the mass of water absorbed over time. We can see that the mass of water absorbed over time is inversely proportional to the square root of the formation factor. This means that the rate of water absorption is also inversely proportional to the square root of the formation factor. And the plot on the bottom right of the screen is a plot of rate of water absorption versus the inverse square root of formation factor, both of which are determined from experiments. As predicted, there is a linear relationship between the two. This brings me to the second takeaway of the presentation. That is that formation factor can be fundamentally related to transport in concrete because it is a microstructural parameter. Therefore, when we measure the formation factor, it's an alternative to performing several ion transport tests like RCPT, bulk diffusion, and sorption. The third goal of my talk is to demonstrate that testing concrete at matrix saturation as opposed to vacuum saturation is more accurate as the measurements are less impacted by air voids. I will also walk you through an example of how we can use the formation factor from a specification effectively. We will learn how to set a job-specific resistivity from the formation factor. The plot I've shown on the screen shows the formation factor of concretes made with three different water to cement ratios at varying air contents. The air content is on the x-axis and the formation factor is on the y-axis. And it's clear that the volume of air voids has a significant impact on the saturated formation factor. So again, the plot on the screen is the saturated formation factor. Let's look at what happens if we measure the same formation factor at the Nick point, which is called the apparent formation factor. Just a reminder of what the Nick point is. It is where the matrix pores are saturated, but the air voids are empty. So in the case of the formation factor measured at Nick point, we can see that the measurements are independent of air, only dependent on the water to cement ratios. Measurement at Nick point has several other advantages as well. I mean, the first one is obviously it's independent of air. The second one is by not saturating the concrete completely and only saturating the matrix, the measured properties are a better measure of the matrix in the system. The formation factor at nick point can also be measured quite quickly, as you just need to immerse it in a bucket of water and you don't need to wait for complete saturation. Let's look at a field example of a bridge deck in Indiana where where I'll show you how we can go from a specified formation factor to a job specific bulk resistivity. So the photo on the left shows the bridge deck during casting, and the picture on the right is the deck after construction was completed. And let me show you an example with some numbers. So let's say there was a job specified resistivity of 1000. The pore solution resistivity can be calculated for the specific case once we know the cement alkali content, the composition, etc. And let's say in this case, we've calculated the cement, the pore solution resistivity to be 0.143 ohm meter. We now have the job specific target resistivity of the concrete, which is 143 ohm meter. And it's just the product of the pore solution resistivity and the formation factor by the definition of the formation factor. The plot on the left is the experimentally measured bulk resistivity distribution for the concrete designed to meet a job specific target resistivity. As seen, it's possible to achieve a target resistivity from a design formation factor. In this particular case, over 95% of the measurements met the design specifications. This brings me to the third takeaway for this talk. 3A, let's say, is it's better to measure parameters at matrix saturation as they are independent of the air content in the sample and they give a better indication of the matrix of the system. Secondly, the formation factor can be used as a good quality control tool. And I've walked you through an example where we can go from a target formation factor to a job specific resistivity. To conclude, today we learned that formation factor is a microstructural descriptor. Formation factor being only a function of the microstructure of concrete is better to specify than resistivity, since resistivity depends on the microstructure as well as several other parameters. Measuring the formation factor is an alternative to performing ion transport tests like RCPT, diffusion tests, and water absorption tests. This is because the formation factor can be fundamentally related to transport in concrete. We also learned that measuring matrix saturation avoids the conductive air voids and gives a better indication of the matrix in the system. And finally, we've shown that formation factor can be used as a good quality control tool and how we can get a job specific resistivity from a specified formation factor for an approved mixture. Thank you. With that, I'd like to yield my time to the moderator and open for any questions. All right. I think there are a couple of questions in the Q&A box. Did you have any problem in using? All right. The first question is: did I have any problem in using a different method to measure electrical resistivity, particularly bulk and surface resistivity? Well, I didn't exactly face any challenges because I mean, it's pretty simple. You just need to take the cylinder out, wipe it with a damp towel, place it between the resistivity electrodes and measure it. But I guess the challenge would be to make sure that you've dried the surface quite well to avoid surface conduction and making sure that the sponges are conductive enough. Thank you for that. And I see another question coming in. Is there development for an ASTM or AASHTO standard for determining formation factor? Thank you for that question. I believe there is an AASHTO standard, TP119, which is for bulk resistivity, and it also outlines how to calculate the formation factor for both the saturated and the nick point cases. To repeat, it's AASHTO TP119.